Okay, thank you. Welcome. Good morning. My name's Martin Nesirky. As you can see, I'm the director of the United Nations Information Service in Vienna, and I was previously the spokesperson for the Secretary General of the United Nations. So I'm sure many of you will have seen The Economist magazine this week. It has a special section this week, in this week's edition, precisely on the future of agriculture, and there's a really heavy emphasis in that section of the magazine on science and technology and innovation. So I think we're on the right track with this session here. So welcome to this interactive lab debate, which is looking, as you can see, at nuclear science for sustainable development. And as the Secretary General, my old boss, said at the opening of this forum just yesterday here, the 2030 Agenda for Sustainable Development and the 17 Sustainable Development Goals are really an action plan for people, planet, prosperity, and peace. And science and technology are really vital components of that blueprint. And so that's what we aim to explore in this session. As I mentioned, if you have the app, you'll be able to use that in two ways. One, to be able to submit questions at any point during the discussion, and we'll have a question and answer session at the end. And two, to be able to take part in a little bit of voting. So, first of all, to find out whether we are sustainably managing our natural resources, we need first to understand much better the environment and the systems that shape the world around us. And we actually know very little about these environmental systems and the interplay between them. But if we are to preserve global biodiversity and halt further losses, we need to understand those dynamics. We need to understand those dynamics right the way down to the level of the atom. And only then can we, with confidence, sustainably manage our soil, our oceans, and terrestrial waters, and food production on land and our fisheries. And these systems are, of course, complex. That's why we don't understand them so well. And climate change is increasing that complexity. And climate change is also producing much higher levels of uncertainty in natural resource management. And that's manifested through increased incidences of drought, of soil erosion, crop failure, an increase in vector-borne diseases in areas that were previously free of them, desertification, flooding, and of course unpredictable weather patterns. And countries are faced with having to assess those risks and manage practical trade-offs without having adequate data and evidence to hand. And this is then further exacerbated by other factors, for example, significant population growth, and that would then require more climate-resistant and high-yield crops. If, for example, we were aiming, as we are, of course, to meet goal number 2 on zero hunger. And so the important role of science and technology as a driver of development has been explicitly recognized for the first time in Agenda 2030, and most obviously in Goal 17. And also, for the first time, it gives a central role to data and evidence. And these will be crucial to guide both the planning and decision-making of national partners and development practitioners. So let's explore how science and technology, and specifically nuclear science and isotope technology, can help understand ecosystems down to the micro level, the level of the atom. So we can then develop better options to manage those systems. And to help us with that exploration, I'm joined by David Osborne and Ana Rafael Callado of the International Atomic Energy Agency, Mohammed Yassin from Morocco, and Andreas Richter from the University of Vienna. And I'll introduce them more fully shortly. But first of all, I need your help. I'm definitely not a scientist. I never was very good at science at school. So we have a little quiz, as you can see. So if you can go to the first question, what percentage of the Earth's land is moderately or severely affected by soil degradation? So you can choose from the app number 1, 2, 3, or 4. So is everybody okay with finding the app? If you don't have the app, you can just put your hand in the air when we get to the end of the 15 seconds. But try voting if you can. Session D2, of course.
How many seconds?
So nobody voted.
So did anybody vote?
I think maybe we were too quick for them.
Oh, yeah.
So, what do you think the right answer is? 50%. We all go to the bottom of the class. Right. So, the next question, how long does it take for a centimeter of soil to form? So, go. Off you go. The excitement is unbearable.
Very
Oh, look at that.
Yeah, very good.
The correct answer is 1,000 years. So the third question. What percentage of human-produced CO2 is absorbed by the ocean? What do we think? Okay, we're getting better. So here's another set of questions. What is the technology bank that is referred to in Agenda 2030? What do we think that is? Are you on your way?
It's counting down.
Very good. Very good. I was sure it was a highly sophisticated financial institution, but okay. Which of the 17 Sustainable Development Goals calls for statistical capacity building? Yes, I think I gave you the answer already, and you're all very clever. Well done. Okay, right. Which of the following challenges are isotopic techniques unable to help address? Off you go. Well, it's tooth cavities. I shall tell my dentist. Right, final question. How many countries are receiving support in addressing development challenges right now through the International Atomic Energy Agency's Technical Cooperation Program? Off you go. Well, as you can see, double the number, almost, 134. Thank you very much. So now we've had our bit of multiple choice, we'll turn to the panelists, and they will definitely not get multiple choice questions from me. So First of all, I'll turn to David Osborne, if I may. And David, you're the director of the International Atomic Energy Agency's environment laboratories in Monaco. And that combination of International Atomic Energy Agency and environment may sound to many people like a contradiction. And some might say that those terms don't fit comfortably in the same sentence. So how do you explain to people why you have both of those terms on your business card?
Thanks very much, Martin, and good morning to everyone. Yeah, this is a question I'm often asked. You know, how do we bring nuclear science and environment into the same sentence? They don't seem to match very nicely. And to respond to that, I'd first of all like to just briefly summarise what we mean by nuclear science. This group did very well in the survey, so they obviously paid attention in science class, unlike yourself, Martin. You'll remember that all elements have isotopes. So the same element can have various isotopes of different atomic weight. The one that most people are familiar with is carbon. Now, the common atomic weight of carbon is carbon-12, but there's also an isotope called carbon-14. In fact, there are several isotopes of carbon. But most people are familiar with carbon-14 and how we use it to date archaeological finds and the like. And that's because that is a radioisotope. It decays over time. So there are both stable and radioactive isotopes. So when we talk about nuclear science, we're talking about the study and use of both radioactive and stable isotopes and applying it to different things. Now, the second point I want to make is that many people are not aware of is that radioactivity is all around us. There are both natural radioactive substances and man-made radioactive substances. This table, you and I, this room, it's emitting radiation all the time. A lot of our food has radiation in it. If you eat some bananas, you're getting a very healthy dose of potassium-40, which is a radioactive isotope. Radioactivity is something that's in the environment and that is natural, and that we need to learn how to use it. But finally, the next point I want to make is that the natural environment is incredibly complex, unbelievably complex. When I talk about complexity, I often like to use the example of a wristwatch. And we all know that a wristwatch is full of little cogs and springs, and how if we can't just go and take one cog out and pretend that our watch is going to keep working. We understand that if you take a spring or a cog out of that watch, it has a domino effect and the whole system shuts down. Well, the natural environment is somewhat similar. You damage one part of it, it has a domino effect and it has consequences across the system. So when we're talking about sustainability, and particularly of food and agriculture and the way we use natural resources, if we don't understand how the system works, if we don't understand that complexity, we won't be able to actually determine whether we're being sustainable. And this is where nuclear science comes into it. So by using the various tools linked to nuclear science and studying specific isotopes, we're able to better understand how the natural system works. For example, there's an isotope of nitrogen, nitrogen-15, which allows us to understand how nitrogen moves through the system, how plants absorb nitrogen at different rates under different climate change scenarios. We're able to use an isotope of lead-210, just the way we do with carbon-14, to do dating and understand pollution histories over the past. We're able to use isotopes of hydrogen, deuterium and tritium, both natural isotopes of hydrogen, to understand where water comes from and where it's going and how long it's been there and those sorts of things. We're also able to use radiation technology for applications that we benefit from all the time, such as sterilising food. Many of you are probably unaware, but you buy strawberries from the supermarket, it's probably been treated with radiation to sterilise it so that it lasts much longer. It's not radioactive. The strawberries you eat are not radioactive. It's just been sterilised because if we don't, it will last only 2 days on the shelf, but we can extend that life many, many more days. By using nuclear techniques, we're able to improve the sustainability of the product. We're able to measure where timber has come from. So, for example, if you go to buy your kitchen floor and the salesman says, "Oh, this comes from sustainably harvested forest," do we really know where it's come from? But by using isotopic signatures of that timber, we're able to determine where in the world that timber actually came from. The same applies to other products like ivory. We're able to develop new crop varieties using radiation technology, the crop varieties that make them more resistant to infectious diseases or to drought and that sort. So there are lots of different applications. The important thing is that nuclear science is an incredible tool for measuring. So and we all know that number one rule of management is if you can't measure it, you can't manage it. So if we're talking about sustainable management of natural resources, we need to be able to measure what's going on. And that's the value of nuclear science. And that's why nuclear science and environment are actually very nice companions.
Thank you very much, David, for giving us this overview from a global perspective. And let me turn next to Mohammed Yassin. You head up the Ecology, Biodiversity and Soil Conservation Service at the Forestry Research Center in the High Commission of Forest, Water and Combating Desertification in Morocco. And so at the country level, Mohammed, contributing to policy making and working closely with national stakeholders, what do you see as the challenges and what are some of the trade-offs you and your government partners in Morocco have had to balance?
Well, good morning, everybody, and thanks to IAEA for inviting me to this panel. I will start with asking you whether you're aware of what we are celebrating tomorrow. Tomorrow is 17th of June, and do you know what is the world community celebrating tomorrow? Anyone know? Any guess? It's World Day for Combating Desertification. And this year's slogan is to protect Earth, restore land, and engage people. And it is calling, I mean, the UNCCD is calling for solidarity to reach the goal of land degradation neutrality by 2030. And in Morocco, we are facing several challenges. And I guess the key words would be to knowing, anticipating and planning all the work that has been done. And in Morocco, Morocco is facing challenges regarding the land degradation and over-exploitation of natural resources. Our resources suffer from, I mean, mainly water resources, are suffering from scarcity and depletion because of climate change. There is, we have a drought that comes frequently. And with regard to agriculture also, the impact of climate change will be a reduction in grain yield production. And the scientists have found that in the future we will have a reduction of in grain yield by 50% to 75% during dry years, and about 10% in normal year. With regard to forestry also, we will suffer from this water stress, and we are, at this moment, we are experiencing some species decline and even mass mortality of cedar atlas. That's the valuable species in Morocco. To cope with all these problems, we have several plans plans for sustainable development. And in the 1980s, Morocco has suffered from a long drought that has had a bad impact on the economy. And the government has decided at that time to build dams. So we have had a strategy to build dams to secure supplies of water and irrigate 1 million hectares by the year 2000. At this moment, we are at about 1.5 million hectares of irrigated land. But that strategy, within that strategy, there was a problem of dam siltation, and we have developed a strategy called le Plan National le Plan National d'Aménagement des Bassins Versants, which is, the National Plan for Watershed Management. And within that plan, the High Commission of Water, Forests, and Combating Desertification has implemented several conservation, water and soil conservation programs, and in about 22 dams. And the plan suggests to implement the soil and water conservation programs on 1.5 million hectares during 20 years. And the High Commission of Water, Forest, and Combating Desertification implemented several conservation techniques like reforestation, rehabilitation of degraded forest ecosystems, improve grazing land, introduce fruit trees, plantation of fruit trees with some conservation techniques, and then construct check dams and wall stones in gullies and rills and etc. So these are some of the strategies that we are using in Morocco.
Thank you very much, Mohammed. And we'll be coming back to each of our panelists for a second round where we may get some more details on this. Andreas Richter, if I can turn to you. You're a professor for ecosystem science at the University of Vienna, of course, in Austria, and you're director of the Austrian Polar Research Institute. I was hearing about your travels both to the polar north and the polar south, to the Arctic as well as Antarctica. So you're a scientist who's strongly involved in fundamental science. So how do you see the role of basic sciences and notably nuclear science in working towards sustainable development? Andreas.
Thank you very much, and good morning, everybody. Well, before I answer your question, Martin, I would like to say that I'm a soil scientist also, and I'm really fascinated by soils. And to develop my point, I would actually like to start with some facts about soils, and then really talk a little bit further. Now, you all know, I guess, that we really heavily depend on soils for food production. More than 90%, even 95%, directly or indirectly, we depend on soils for food production. That's really important. And the second thing that I want to say is that many people are not aware of, soils regulate, filter, and also transform nutrients and type of contaminants in soils, so that we actually have clean water to drink. So it's really, these are the two major functions that we actually have. But I will concentrate now on the third one, and this is now coming back to the Arctic and to the other stuff. Soils store a really high amount of carbon. Yeah? We sequester the carbon over millions of years, and today we have roughly 3,000 billions of tons of carbon stored in soils. And to set this in perspective, we have only about 800 billions of tons of carbon in the atmosphere, and only about 600 billions of tons of carbon in the vegetation. So we have more than double the amount in soils than we have in the atmosphere and in vegetation together. Now, why is that important? Because half of this carbon, a little bit less than half of this carbon, is actually stored in permafrost soils. Soils in the high north, which are permanently frozen. Now, and this is now important because, as you know, permafrost soils get warmer and warmer, and they thaw. And if they thaw, this carbon may be vulnerable for decomposition by microorganisms that actually produce CO2 and methane out of this organic carbon in soils, and this will be then, redistributed to the atmosphere, or it could at least be. Now, this is a very dangerous type of scenario, because if we could redistribute a lot of this permafrost carbon to the atmosphere, we could eventually increase the atmospheric CO2 concentration dramatically. And so scientists have looked into this for a long time, and in the last IPCC report that you may have read already in the fifth assessment report, scientists were very careful to actually formulate it, and I have just put it out. So what they said is, it is virtually certain that permafrost will melt, and it's already melting in many parts, and that part of this carbon becomes available for decomposition. But they also say that we only have a low confidence, so low confidence is the word here, that soils are really becoming net emitters of CO2 and methane. So I'm saying this because we have a high uncertainty here that we need to address. And why that's so important, I just want to tell you, the models that we have show that up to 400 billions of tons of this permafrost carbon could be actually liberated by the year 2200 to the atmosphere. And that would increase the carbon concentration by roughly 200 ppm. So now we have 400 ppm of CO2. Let's imagine we have 200 ppm more just because of the permafrost carbon that would come to the atmosphere. That would be type of catastrophic, or could at least be. So the strong feedback, we have to research into that, and we have to get a good estimate on what it would mean for the warming, for global warming, for positive feedback to global warming. And for this evidence and evidence-based data are really important, and we need to constrain better this vulnerability of the carbon pool in the Arctic. Now, this is done worldwide in many cooperation projects. One of those is actually also by the International Atomic Energy Agency. That's an interregional project where 23 countries are actually working together, and I'm the Austrian representative of this. So we are working together in constraining the carbon that could be actually coming to the atmosphere in the future climate. So my point that I would like to make in the very beginning here is that science, and I do see us like that, for sustainable development means that we need to provide independent, evidence-based type of data for decision makers and for the society. That's the most important goal for us, I think.
Thank you very much indeed, Andreas. Let me turn now to Ana Bravo Callado, and you're a director in the Department of Technical Cooperation at the International Atomic Energy Agency. So we've heard how isotopic and nuclear techniques can play a role. So how would you respond to the criticism that one sometimes hears, or the comments that one sometimes hears, that such techniques can only really ever play a niche and very specific niche role?
Thank you, Martin, and thank you everybody for being here this morning with us. I respond to that with the explanation that the IAEA is indeed a specialized agency. We do work with atoms for peace and development. That's our logo on our business cards currently. I wanted to talk a little bit about how we wrap up together this science that was just described by my colleagues. The agency, the IAEA, has in numbers today, just to give you an idea, we have 167 member states, as you saw from the questions. 134 of these member states work with us in technical cooperation. Of these 134, 35 are least developing countries. So 95% of the member states that work with us in technical cooperation are developing countries. We address the needs of these countries. They come to us to ask for a solution. They come to us to ask for assistance. We don't claim to resolve the problem because of this specialized nature of our work. And that's why it's so important for us to partner with other organizations. As Professor Yassin was mentioning, UNCCD, for example, is one of our partners. Our projects go to the field. We work with the member states in the field, but we don't have field presence. We're not an agency that has local offices. So we desperately need to work with partners if we are going to deliver a product and provide sustainability to our member states. This is very important. And in that regard, I can list a few of our partners that you may already know. So the Food and Agriculture Organization, FAO. FAO has been our partner for so many years that we actually have a joint division with them. It's the IAEA FAO Joint Division. WHO works with us very closely in cancer treatment. UNDP, UNEP, on environmental issues, and as Mr. Yassin mentioned, UNCCD. Without these partners, there's no way that we as a specialized agency can claim to have sustainability in the field. We need partnerships. Another point that I would like to mention to you all is how quickly we can respond to a call from our member states. I don't know if you're all familiar with the outbreak of the Zika virus, and last year with the Ebola outbreak, member states came to the IAEA asking us to act immediately. And we did, but we did that with partners. So in addressing Zika, and if you all visit our stand, and stand number 21, you will see some more practical examples of what I'm saying. We had to partner with WHO on that. And we went back to the countries and we sat together on how we could address immediately a solution for that outbreak. The same thing with Ebola that happened last year. So basically, we meet, we work with our member states. We don't claim to resolve the problem, but we address their development goals, their national development capabilities, and we work together with them in terms of delivering and transferring technology for their sustainability and development. Thank you.
Thank you very much, Anna. I'm going to stay with you, if I may, for a second, and perhaps dig a little bit deeper and pick up on the last point that you've made about working with partners, and particularly in developing countries. How do you ensure that knowledge, that expertise is transferred to the people in those countries, in so many countries? How do you ensure that they are then able to use the information, use the expertise themselves?
Okay, I still have this on. Yes, transferring technology and transferring or delivering services. We do that in a very planned and strategically thinking mode. We don't just grasp the partnership out of nowhere. It needs to blend with us. We need to have a very tight connection, just so we have with FAO and WHO. When we transfer these technologies and we deliver our services to our member states, we strongly believe that we're making a difference. And again, what David Osborne was just mentioning, the drive to pursue accurate data is what brought us to this venue today. We have a strong belief that the IAEA is part of this global effort. We come in with a highly specialized group of individuals, not only at the agency but outside. I mean, we have contacts with experts, just like Professor Richter here. We work together with all these experts. And collection of data is key for us in this development discussion. We can provide accurate, fast data for decision-making politicians in the countries and even in research institutes as well. So I would say that that's our specialty and that's our contribution. I want to give an example of one of the things that we worked with in terms of erosion, soil erosion. We don't need to wait multiple harvest periods to understand how a soil moves. We can do that with our tracing isotopes. And that's so accurate that it saves time and we can actually make a difference. Yesterday I was talking to, I see him here in the audience, I was talking to a gentleman that was working in Zimbabwe. right? And he was questioning. He works in identification of water in certain places. And one of the issues that he has is that they dig wells, and then here comes the soil and covers everything. So we work in that sense as well, tracing how the soil moves and making sure that you can make the best out of the work that you're doing. We also identify where water is. And we have a project called the Sahel Project. It's an interregional project, so it involves multiple countries. And this project not only identifies where the water is in that region, but also the quality of that water. We can do that with nuclear technology, nuclear techniques, and this is what we bring. So together with other organizations, we would like to move on and really provide a sustainable product solution to our member states.
Thank you very much, Anna. And so we can turn actually to one of those member states, also with a Sahel connection, of course. Mohammed, if I could return to you. So we've heard about the abstract, if you like, the scientific side. We've heard about the very practical applications. So perhaps we could also delve a little deeper with you. Tell us a little bit about working on the groundwater basin and what you've already described about the dams and siltation and so on. What difference has the work that you've been doing using these techniques had in the lives of Moroccans?
Yeah. As I said, the High Commission of Water, Forest and Combating Desertification is implementing conservation techniques over a number of watersheds. And in our, well, to continue to do that, it has to prove the efficiency of the work. And in our, in the Forestry Research Center, to which I belong, we developed a method, a holistic approach to assess the impact of all those watershed management techniques, mainly in 2 pilot watersheds. And within that holistic approach, we integrated quantitative methods to assess the impact and others that are qualitative. The quantitative methods include the radiometric measurements and hydrometric stations. And when we have conducted the experiment, we were delighted by the results that we got from the isotopic measurements, because in a quick time, by using the beryllium-7, we were able to assess and see how much soil erosion was reduced by those different techniques that we have been using. In other, the isotopic measurements was better than the others because we could have good results and with statistical analysis that have proved the efficiency of those techniques. And we found that, like, reforestation reduces erosion by 35%. Rehabilitation of degraded forest ecosystems also reduces erosion by about 40%. Planting tree fruits also reduces erosion by about 45%. And just fencing and forbidding the grazing and letting the land to recover was able to reduce erosion by 60%. The check dams in gullies and wall stones have reduced erosion by 65%. All these figures give some help to decision makers that they can argument to ask for more financial support to keep on doing these techniques. So I think the isotopic method was of great help, because with hydrometric stations and other modeling, we need much more time to have effective, good data to analyze and and have results for all those techniques.
Thank you very much, Mohammed. Andreas, I'm going to come to you and zoom back out again, if I may, from looking at Morocco to a global view. The World Meteorological Organization this week has been reporting on global temperature trends again, and it seems that May this year was another record-breaking month for temperatures, and particularly in the Arctic North. So as we seek to implement the Sustainable Development Goals, and obviously in this context we're looking at number 13, but not only. So what's your main concern here?
Well, yeah, thanks for the question anyway. Well, my main concern certainly is that climate change is likely to create new risks that we really don't know about, and that is actually amplifying risks that we already know, but that we cannot, predict properly. So I will just give you an example, and I want to start where I have actually ended with my last few words that I had. So I have showed you that there is a lot of carbon that is maybe vulnerable in the future climate to actually have a positive feedback on climate change. So we may lose carbon from permafrost soils. But on the other hand, and that's more important for the moment, is that soils like the oceans, like we've heard before, are sequestering carbon at a relatively high rate. So if we would not have soils and the ocean and vegetation to take up carbon that we have actually emitted to the atmosphere, we would have much higher carbon concentrations already. So only about 40% of the carbon that we emit actually ends up in the atmosphere. Would we not have that, oceans and land ecosystems taking up equal parts of it eventually, we would have carbon concentrations of around 170 ppm of CO2 in the atmosphere, higher than we have today. That's really a lot. Yeah? So we would have much warmer conditions. So it's important that we take it up, and that's beneficial. So soils, vegetation, and also the oceans are beneficial in a way in taking up this additional carbon. On the other hand, and this is like a little bit unexpected, this sequestration of carbon in vegetation and soils has also unwanted type of consequences. For example, if you increase carbon in soils and in the vegetation, it also increases the nitrogen, phosphorus, and other nutrient content of soils, for example. But these nutrients are then not available for plant production again. Right? So it sequesters not only carbon but also nutrients, and that's a big concern. It actually led to the observation that under elevated CO2 we have, for example, less protein content, because protein is nitrogen rich, in food crops. But I would like to give you another example, and that's one that just recently in 2014 has been set out. So we know that zinc and iron are very important micronutrients for humans, right? We know that about 2 billion people currently are actually have deficiencies in these zinc and iron concentrations. Now, what happens now is that it has been shown that under elevated CO2, stable food crops have actually decreased the content of iron and zinc. And that's a very dangerous situation. We already have 2 billion people suffering actually from this, especially developing children. And now we have a situation where elevated CO2 concentrations could even reduce those micronutrients further in foods. And we have to combat that. Yeah? And my point is I don't have an answer how we should do that. There are several possibilities. But the point is we have to see the big picture. And in this case, the big picture is a global change that we have, a global change of the CO2 concentrations. Global warming, as you have said before, is also changing that. We don't really know whether global warming would enhance again the decomposition, so we don't really know how this is balanced. But we need to put an emphasis on research in this area, and actually without isotope that's completely impossible. Yeah? looking into sequestration of carbon, for example, needs to work with stable isotopes and the radioisotope 14C. Without that, it's not possible. So I would really want to say climate change has a lot of potential to create new risks that we are not aware of at the moment. We need to research into that, and I'm pretty sure that the risks that they are coming are greater for disadvantaged communities or people. They are not so much a problem for the people in Western Europe, for example, because we have possibilities to adapt, but people in other countries won't, not that easily. And I think it's really our duty to do more research in this area. Also basic research. I don't say that we only need to have applied research. I think blue sky research sometimes is necessary to see things that we have not thought before, right? So that's my point that I would like to make.
Thank you very much, Andreas. And from the land and from blue skies, let's turn to the blue oceans. David, what's the picture like under the water?
Thank you very much, Martin. This actually is a really important point because we've been talking about a lot of issues that are relevant to many of the Sustainable Development Goals, but Sustainable Development Goal 14, which applies to life underwater, and that is very dear to my heart, so thank you for that question. As Professor Richter was just saying, climate change brings a lot of uncertainty. And the way scientists try to deal with that uncertainty is by developing models. And obviously, models need to be refined over time. The more we understand how a system works, the more accurate a model can be, and the more we can start to predict what the impacts will be. That's relevant, directly relevant to development, because there's no point investing in an area if that investment is going to be wasted or the ecosystem is not going to support it. So we need to understand how the system's working, and the oceans here are critical when it comes to climate change. As we've heard, the oceans absorb as much CO2 as forests, for example, and just like forests, the ocean breathes, releases CO2, it absorbs CO2, and some of that CO2 gets exported to the ocean floor. So the carbon binds to particles, or it gets caught in the shells of microscopic plants, and it falls to the ocean floor. We call this marine snow. And you'll all be familiar with the White Cliffs of Dover. That's an example of carbon that had from millions of years ago that descended to the ocean floor, that was exported out of the atmosphere. The oceans continue to do that. We need to understand how that's happening, and by using radioisotopes, particularly in the uranium-thorium series, we're able to analyse how quickly that carbon is being exported out of the system, and understand how climate change and warming seas, changes in stratification, ocean currents, etc., are being affected, and therefore affecting how much carbon is coming out through the oceans. Linked to that, there's the problem of ocean acidification, because as the carbon is absorbed, it changes the chemistry of the ocean, and that impacts on the ability of marine species to absorb calcium carbonates and to form their shells. It also impacts their behaviour, it affects their reproduction. There's a whole number of impacts as a result of ocean acidification. So using a radioisotope such as calcium-45 or isotopes of boron 12 and 13, we're able to understand this process and what's happening in the natural world, and therefore improve these models. This is what all of this research is about improving our understanding of how the system works. And the more we understand how the system works, the more confident we can be in our development investment.
Thank you very much, David. Well, that's a perfect introduction to the question and answer session. And I have a question here from Gerhard Rappold. He's from the Deutsche Gesellschaft für internationale Zusammenarbeit, the German development agency. And he's raising precisely the point about the importance of data, but how do you make it usable for end users? How do you make it digestible? So it's all very well to have data, but how can you make it ready to use? For example, from having that data to having a service, so if you like, a kind of a production chain. Would you like to pick up on that, David? And perhaps our other panelists, and I think Anna would like to jump into.
Sure, thank you very much, Martin. One thing I didn't mention when it comes to the oceans is that we maintain a global database of marine radioactivity. And we've been maintaining it for decades now, monitoring radioactivity and from across the globe. And this is really helpful in helping us to understand both the levels of activity and the decay rates and so on, but also oceanographic processes. We can analysing that data, we can see how the ocean moves and where currents are going, and in 3 dimensions. And so it's very, very valuable in that. And we're actually struggling with this issue at the moment is we provide the data in a very scientific, technical format, and scientists who are working in that field are able to access the data. But we're now trying to develop that data into information that can also be used for policymakers. Because we understand that policymakers aren't oceanographers, they're not radiochemists, they don't understand necessarily the data in its raw form. So the challenge is presenting that information in a way that can be used by both the scientists in a very raw format through to processed information for policymakers and the general public. And that's an ongoing process.
So Anna, did you want to jump in there?
Yes, I do, and I'm going to speak here with my colleague next to me about the project on climate change. Exactly what David just mentioned. I participated in the scoping of the climate change interregional project, and I love my colleague scientists, but I'm not a scientist myself. So my participation in that project was to ground them and collect that information, and how would we transform that information into important source to policymakers. And this project actually is a good combination of that, because as Professor Richter and many other scientists collect samples around the world in these databases or benchmarking areas, that information is going to be collected, it's going to be intercompared, and it's going to produce probably a model to present to decision makers. So we collect the science, package, and transfer to member states and also to policymakers. And the Climate Change Interregional Project is a very good example of that.
Thanks very much, Anna. So I'm just looking here. Joseph Molambo, could Andreas Richter clarify his statement on the relationship between carbon dioxide and the availability of iron and zinc in staples? And then if you other questions in the room, please do raise your hands, of course. Andreas.
Yeah, there have been several studies, and the last one in 2014, which was published in the journal Nature, and clearly showed that it was a type of a meta-study where many different studies were put together and were specifically analyzed for the concentrations of zinc and also iron and other micronutrients in the seeds of, for example, in this case it was legumes, I think it was peas, but also other legumes, and it was wheat and other type of staple foods, right? And they looked into the concentrations, and if the plants were grown in elevated CO2, between 500 and 600 ppm of CO2, now we have 400, and then the concentration of zinc and iron was actually lower in those crops. Not so much, but about 10%, which is quite a bit. If you have already, communities that depend heavily on rice, wheat, and legumes, that could be a potentially intensifying the problems that we already have for zinc and iron content in those foods. Certainly, there are also other things that they found. For example, and this is also one of the reasons why this may be a bigger problem in the future. You have in some of those seeds, you also have phytate. Phytate is a chemical component that is sugar-like and has a lot of phosphorus in. And if you have an increased phytate concentration, then the resorption of iron is lower. And that means if you have an increase in this concentration, you even if the iron would be there, you cannot resorb it properly. And that actually also was increased, at least in some of the crops. Right? So we may have a multiple problem. We have more phytate, we have less of iron and zinc and other micronutrients, and that may be could create a very dangerous situation. And now what we need to do is to clearly see whether other components maybe in those foods are actually enhancing the resorption. We don't know that. So we need to research into the resorption, into how much is actually lost again from the human body, and things like that. So this is not an easy question to solve, but at least it was shown that the potential that climate change, in this case elevated CO2, could reduce, like the iron and zinc nutrition of a lot of people. This potential has been clearly shown.
Thank you, Andreas. Joseph Molambo is from Harvest Plus, so obviously there's a very direct link there. So I'm looking for other questions or any follow-up questions that there might be. Please. Yes, please. Perhaps you'd like to introduce yourself.
Yes, hello. Thank you for the very inspiring panel discussion. My name is Alexander Käfer. I'm from Germany, University of Marburg. And well, the first idea which came into my mind when reading the title of this panel was what sustainable development might have to do with nuclear energy. So I'd like to ask you, and probably you're waiting for this, how, given the fact that there are so many developing countries asking for advice, as I just learned, 95%, how nuclear energy plays a role in this context.
Okay. Yep, please. Anna, or David, would you like to take that?
Go ahead.
Okay, thank you. Thank you very much. It's a very good question, and we all know that energy is an important part of development. It's captured in the SDGs. How countries move towards their energy production is for countries to choose. Obviously, many countries, or in fact all countries, have a combination of energy supply mechanisms. The IAEA does not advocate nuclear power. We're not pushing nuclear power down the throats of the member states. But what we do is support those countries. If a country chooses to include nuclear power as part of their energy production cycle, we work with them to ensure that it's done safely, that it's done in a secure way, and that it's done in a sustainable way. I think that's the basis of what we try to do. We're saying we acknowledge this is a technology that is available to you. We're going to help you to do it in a safe way.
Please, Anna. Yeah.
Yes, and adding to what David just mentioned, we don't sell nuclear power, but we have numerous calls from our member states to support them in building up their regulatory infrastructure, and as David mentioned, to make sure that they do it in a safely manner. So this is our contribution. We have several projects. The IAEA has several projects in international and technical cooperation that addresses regulatory capacities and also licensings. So that's how we contribute to that goal.
David?
Yeah, sorry, I just wanted to add, this point that your question is a natural one that we often experience, because that is what people associate with the IAEA. And one of the things we're trying to communicate through this event is to demonstrate that the applications of nuclear science and technology goes far beyond nuclear power. And we've talked about many of the applications, but we haven't even touched on health in a substantive way, in terms of radiation oncology and things like this, or nutrition management.
Obesity.
Obesity. Anna touched on Zika and Ebola just slightly. There's so many things in this limited time frame that we haven't even had the chance to address. But what we're trying to highlight is that there is the word nuclear is much bigger than just nuclear power.
Mm-hmm.
Okay, and other questions, please? Yes, please. The microphone's coming.
Thank you. Thank you very much. I must say I found this entire session very interesting indeed, from the mineral content of crops to my particular interest. And thank you. The movement of soil particles from the watersheds in Africa, for instance. From Zimbabwe, there are entire archipelagos of islands being created in the Mozambique Channel from loss of topsoil. Check dams, thank you. My particular interest. Dryland areas, we have the river channels.
Could you hold the microphone a little bit closer?
This is quite a good example. Take this as a river channel. Many river channels are about this wide and they're this deep, full of sand, and the sand stores water. Where the river channel is narrower and the sand is maybe only this deep, there's not a perennial supply. I'm interested in constructing sand dams, check dams. What I need to know is what the distance that a grain of sand will travel into that, because it affects very much the way we construct the dam, how much, what height we construct it. Now, we're just a little one-off NGO in Zimbabwe. I don't see how we work with you, but you mentioned partners, FAO something. Can I link up with FAO to get some assistance? For you to tell me how far that grain of sand travels in a year, is it meters or is it kilometers? I don't know. It would be very helpful. Thank you.
Well, just before I turn to the panelists, certainly if there are any specific questions where there can be follow-up, I know that my colleagues afterwards will also be very happy to talk to you separately to look at some of the details that arise. But I don't know if David or Anna, perhaps Anna, if you would want to respond to that right now. And then we'll have time, I think, for one more question, which I have here on the iPad. And we'll see if there's another question from someone putting their hand up as well. So please, Anna.
Right. I think that from what I understood, and this is basically the conversation that we had yesterday, our contribution, and I don't want to dwell much in the technicalities of the work related to FAO and us, but we do have techniques to trace movements and to make sure that the soil is ready for that type of activity that you were just mentioning. I think that the best thing to do is, instead of us discussing the technicalities here, is I invite you for a cup of coffee, and maybe we can talk some more about that. And I can introduce you to my colleagues in the joint FAO IAEA division who are in stand 21. Okay?
Thank you very much. Okay. Sounds like a deal. Okay, so I have a question here. Any research, this is from Asakarlinios Pasan. Any research to support sustainability of crops in developing countries such as coffee and palm oil? I don't know if you're aware of any of those.
Are you ready to do it?
I am not aware if my colleagues in the Food and Agriculture Division have specifically focused on coffee or palm oil. That is possible. So the person who asked the question, if you give me your details, I can find that out. Because of course, we do a lot of research on a number of different crops, and in that includes creating new crop varieties, as I mentioned earlier, with resistance to stresses such as disease and climate change and so on. But whether they've done specific work on coffee or palm oil, I'm not sure, so I'd have to follow up on that.
Please, Anna.
The work on coffee, I was actually driven to the stand that talks about cocoa, and there's a chocolate here. I thought that was very interesting. I would advise you to go into our website, IAEA.org, and we have so many success stories published on our website. And you may find some very useful information, maybe not particularly with coffee, but another grain, and maybe we could talk some more and exchange some emails about that. So our website is extremely rich in information, and I'm sure that you can find some very enlightening responses there too.
Rice in Vietnam is one example.
Rice in Vietnam was a project that was very successful. We helped them with the issue of the soil being saline and how the rice crop could survive that environment. And it was such a successful project that now other countries in the region are importing that technique as well. So all of these stories, success stories, we have them published on our website.
Thank you, Anna. So I think we need to be wrapping up at this point, and obviously my colleagues here would be very happy to take more questions after the session finishes, should you have them, of course. So let me go first of all to Mohammed. Perhaps you'd like to summarize in a couple of sentences what's your key message. What would you like people to remember and to take away?
Well, I don't have really a message for the audience. I have just been thinking of something to propose to IAEA. At this moment, the High Commission of Water, Forest and Combating Desertification is reviewing the National Watershed Management Plan. The National Watershed Management Plan was approved in 1996 for 20 years, and at this moment the High Commission is revising the plan with support from the European Union. And I really hope that IAEA may be integrated in that revision, because we have seen that the isotopic methodologies can be of great support to prove the efficiency of the conservation, the water and soil conservation techniques, and this can help really much in improving and convincing the financial agencies to support the watershed management plan in Morocco.
Thank you. That sounds like something that David and Anna need to take away. Thank you very much. So, Andreas, what's your 30-second message?
30 seconds, okay. Science must really provide independent evidence and data. That's the most important thing that I want to emphasize. And it's not that we need so much more research in sustainability itself, but we must make the research available for those that actually then try to create sustainable or to get the sustainable goals working. So climate change will likely create new risks, and we need more science to actually address these risks in the future.
Thank you, Andreas. David?
I'll come back to my metaphor that I used at the beginning to refer to the wristwatch. And I have in my mind's eye this old guy from Switzerland, staring through big magnifying glasses, doing very precise, he's a skilled artisan doing very precise work requiring a lot of patience to put this watch together to make it work the way it should work. And that's what we need in the natural environment, is a very good understanding, a lot of patience and understanding it, very precise knowledge. And that's what nuclear science is. Nuclear science equals precision science, which equals better environmental management, and which is therefore more sustainable management.
Thank you, David. Anna?
Okay, my 20 minutes. 20 seconds.
20 minutes.
Oh, I can talk for 20 minutes easily. I just wanted to say that we at the IAEA, and I'm guessing all other scientists, are extremely happy with the fact that the Development Agenda 2030 has incorporated science and technology into the discussion. Today, the IAEA and our colleagues are here to present ourselves as part of this solution towards development and towards sustainability. We are a part of the team. We need to be able to join forces and really address this very ambitious agenda that drives us together in the collection of data and accurate information. And just to wrap this up, it's really important that we continue to invest in our youth, forming new scientists for the future, focusing on STEM, and really looking into gender equality as well, promoting women to study science so that we can absorb them at the IAEA. So thank you very much.
Thank you very much, Anna. I think that's
There's a question.
Oh, there's a question.
No. Thank you very much for the question. I know that Anna would like to briefly respond before we wrap up. Yeah.
Yes, muchas gracias por tu pregunta. Just very quickly, as I mentioned to you, the IAEA works with several countries, and there is an entity in the country that is our focal point. So that is the channel of communication that we have to establish first, and then seek the solution and discussion for the problem that you just raised. But we need to but I need to talk to you separately. And for anybody else who is interested here, because we're running short of time, I can walk you through how to engage with the IAEA. It's not complicated. It's just finding out who your focal point is and introducing yourself to him or her. And this person will be talking to the IAEA and transferring to us the demands and the needs from Peru in that case.
Thank you, Anna. And I'd like to thank all of our four panelists, David and Mohammed, Andreas, and Anna, for giving us a really, I think, a crucial overview and some really clear insights into the use of nuclear science and what this looks like in practice.
I forgot to show this.
Oh, please do.
I forgot to show this. This is our brochure of how the IAEA supports the Sustainable Development Goals. It's on our website. It's quite interesting. It lists 9 of the goals, wrapping up with this goal 17, which is what we talked about here, partnerships and joining forces. So I encourage all of you to go on our website and read this brochure. This is a paperless event, so I wish we could distribute, but we can't. So I'm giving you the map of the treasure to go after this information. Thank you.
Sustainably available online. And as the Secretary General said just yesterday, we must make the best use of science and technology and innovation if we are to really succeed over the next 15 years. So thank you very much to you for your questions and your interest. Thanks for coming.
Thank you.